Today we are going to discuss about solids, that is how the constituent particles of solids are arranged to give some special property to the solids like rigidity, less compressibility, high density and definite volume and definite shape. Now we will see the arrangement or the packing of close packed arrangement of constituent particles in one dimension. Now in one dimension, the solid particles are assumed to be spheres and they are arranged very close one after the other, resulting into the linear type of arrangement, also called as linear arrangement or linear alignment, and it results in the formation of the edge of the solids or edge of the unit cell. Now let us come to close packing in two dimension. In two dimension, there are two types of arrangement. First one is square close packing. In square close packing, we will see there is spheres are arranged linearly one after the other, forming the edge. The second line is vertically aligned, one sphere after the other. Third one again vertically aligned with the previous layer. In this way, you will see that the spheres are arranged one after the other, and in this type of arrangement you will see the close packed arrangement. There is a square type of a empty space between them. This empty space which is present is called as square void or square hole. Now coming to hexagonal close packing. Hexagonal close packing, in this you will see the edges or the first line is formed just like the previous one sphere after the other, forming the edge. Second spheres are seated in the, that is the gaps between the previous layer, depressions of the previous layer. In this way you are forming the successive layer one after the other. Now in these layers there will be triangular voids, 50% pointing upwards, 50% pointing downwards, and this type of a packing is called as hexagonal close packing. Now in solids, because they are to be packed efficiently, the square close packing will be rare. Hexagonal close will be the most frequent one. Now we will proceed to the close packing in 3 dimension. How the particles are packed in 3 dimension. In 3 dimension, if we extend the square close packing, that is A, we will see one A layer, another A layer, third A layer. All these layers will result in the formation of a very simple cubic close packed arrangement. In this case, in 3D, there will be some empty space which are formed. Now these empty space will be called as cubic voids or holes or body centers, we will see later on. But this type of arrangement where only A are present will be called as simple cubic close packed arrangement. Now let us see how this hexagonal close packed arrangement proceeds in 3 dimension. Again here there are 2 types of packing of the layers, that is AB type of packing, that is hexagonal close packed arrangement, and another arrangement is ABC arrangement, also called as cubic close packed arrangement. Now what is this AB arrangement? We will see that is in AB arrangement or hexagonal close packed arrangement, you will see there is a layer red colored, then we have second layer B layer with blue spheres. Now this is present on the triangular voids of the first layer. Now third layer, again we will see third layer is vertically aligned with the first and fourth is vertically aligned with the second. So in this way first and third layer is same, second and fourth layer is same. We call it as AB type of a packing. Now see here, we can see in this figure, this is first layer, second layer, third layer. First is same as third one, A, B, A. Likewise, such type of arrangement we will call it as hexagonal close packed arrangement, AB type of packing. Now coming to cubic close pack arrangement, the cubic close arrangement, that is ABC type of packing, it will be little different from the previous one. But the basic packing of HCP will be same. This is the first layer, red one you can see here. Now in this layer there are A types of voids, triangular voids pointing upwards. You have got B type of voids, that is the voids pointing downwards. Now I want to place a second layer over it. Now the second layer I will be covering, you can see here I want to cover, I am covering A. Now second sphere I want to put, I cannot cover B. You can see here I have to cover A only. That is, at a time either I can cover A or B. Both the types of voids cannot be covered while forming the second layer. Now I am forming the second layer with the black spheres covering all A type of voids of the, that is the triangular voids pointing upwards. So I can see this is my first layer AB, AB. I am covering the A voids with the black type of spheres. Now when I have formed the second layer, I can see I have covered these A voids. Now this void, there are 4 spheres in contact. Now this will be special different type of a void. In 3D you will have different voids. Here you can see the B void of the first layer. Again it is overlapping with the void of the second layer. Now here this void is surrounded by 6 spheres in contact, red, 3 red and 3 black spheres, whereas this void was surrounded by 4 spheres, 3 red and 1 black. So there are 2 different types of voids. Now these 2 different types of voids are called as tetrahedral voids. Tetrahedral void you can see is formed by 4 spheres, 3 blue, 1 red. This enclosed space is called as tetrahedral hole or tetrahedral void. You can see here, when the definition comes, you have to specify that this is the space enclosed between the 4 spheres in contact such that the center of the sphere lies at the vertices of the tetrahedron. You can see tetrahedron has got 4 vertices. So definition you will write down accordingly. Now another type of void which is there is octahedral void. Now octahedral void is a void between how many spheres? 6 spheres. Now you can see here 3 blue ones and 3 red ones. This is the first layer, this is the second layer spheres. Now these 6 spheres are enclosing the space called as octahedral hole or octahedral void. Now when you want to define, again the definition will be just like tetrahedral void. It is the sphere, that is the space enclosed between 6 spheres in close contact such that the centers of the spheres are at the vertices of the octahedron. You can see octahedron has got 6 vertices. So accordingly you will define the void. Now you can see I have formed 2 layers A, B. Now I want to place the third layer, that is the C layer. Now C layer I want to, that is, you can see this white layer or the C layer is there, third layer. It will generate C types of voids. These are the octahedral voids of the second layer. B voids were the octahedral voids of the first and second layer. So in this way we are able to see third layer formed is different from the first initial 2 layers. So this is the C layer. So the packing is ABC type of packing, results in the cubic closed pack arrangement. Now if we see here the layer A, then we have layer B, then we have layer C. A, B, C, again A. So ABC type of a packing is also called as cubic closed packing. ABC. In this way first and fourth layers is same. Now the voids which we have come across in this closed pack arrangement in 2D, we have got 2 types of voids, triangular voids and square voids, which we have seen earlier. In 3D we have got tetrahedral voids and octahedral voids. These tetrahedral and octahedral voids will be seen in hexagonal closed pack arrangement, whereas cubic or body center will be seen when there is closed packed arrangement of square arrangement. That is, when square arrangement is closely packed, we will come across cubic type of arrangement, which will result in the formation of simple or primitive type of the unit cells. Now we will see the different types of unit cells and how they are arranged, how many atoms per unit cells are there, likewise. Now this is the simple cubic unit cell. You are able to see vertices are occupied by the lattice point. These are the lattice point occupied by the 8 spheres. Now these 8 spheres, we will find out the number of atoms per unit cell. You can see here the sphere at the vertices. This is shared between 8 neighboring unit cells. So the contribution of this is 1/8 towards this unit cell. So as the spheres are present only at the corners, the contribution comes out to be 8 into 1 upon 8, that is equal to 1. That is why the value of Z, that is the total number of spheres in simple cubic unit cell, is 1. The value of Z will be 1 for simple cubic unit cell. Now coming to another type of packing, that is body centered closed packing. In body centered cubic arrangement, you will see that the lattice points are present at vertices and there is one atom at the body center, the black sphere which we saw in the earlier slide. Now we want to carry out the calculation for number of atoms per unit cell in case of body centered arrangement. Now this is the body centered arrangement, 8 corners and 1 at the body center. Now let us see the contribution. We will see vertices, it will be 1 upon 8, but this sphere is totally present inside the unit cell. Now this particular is 100% occupied within the unit cell, so contribution will be 1 or 100%. So contribution made by the corner sphere is 8 into 1 upon 8. Contribution made by the sphere present at the center of body is 1. So total number of atoms or spheres in BCC comes out to be 1 plus 1, that is equal to 2. So number of atoms per unit cell in body centered is 2. Now coming to face centered cubic lattice, you can see face centered cubic lattice is the one in which there is a lattice point located at each of the faces. So there are 6 additional spheres in here apart from the 8 vertices. Now we will work out for this also. Now the simple diagram you can visualize over here. For number of atoms per unit cell, we will calculate contribution made by the corner spheres will be 8 into 1 upon 8, that is equal to 1, and contribution made by the atom at the face will be half, because 50% sphere will be in one unit cell and 50% will be in the another. So how many faces are there? 6 faces. So 6 into 1 upon 2, which is equal to 3. So total number of atoms or spheres in FCC unit cell will be 1 plus 3, which is equal to 4. So in this way the value of Z comes out to be 4 for FCC type of arrangement.